Okay, so it is now time to talk about the double angle identities. To begin with, I'd like to share where these identities can be derived from, and then in a little bit we'll use them in the context of the trig aspect of precalculus. So first of all, a good starting place for the double angle identities would actually be to look at the sum and difference identities, which we've seen already. And taking the sum identity for sine and cosine, we can use these to arrive at the double angle identities. I'll show some steps on the next slide, but just to refresh you on the look of these sum and difference identities, let's begin with the sine of a plus b identity. So this is the sum identity for sine. And in order to arrive at a double angle identity, what we're going to do is just make sure we're inserting the same angle twice. So in the current sum identity, we have angle A and angle B, which we typically treat as two distinct angles. But what I'm going to go ahead and do for our purposes here is input A and A as the two angles. And then we'll just follow through the formula with that understanding. So just to make it a little bit more clear, anytime I see A, of course, in our original sum identity, we'll have A. Anytime we see B in the original sum identity, we'll be replacing that with A, because what we're saying now is we're putting angle A in twice. So as we do that, that'll give us sine of angle A times cosine of angle A again, plus cosine of angle A times sine of angle A. And what we notice as we input that sum identity with angle A twice is we end up with the same term, meaning that sine of A cosine A plus cosine of A sine of A, those are really two like terms. Just to make sure that point's very clear, I'm going to take a brief moment and rewrite the second term. The order of multiplication doesn't matter, so I'm just going to express that as sine cosine. And that should allow us to then conclude we've really got two of those terms. So this simplifies to 2 sine A cosine A. And on the left-hand side, if we were to clean up sine of A plus A by again collecting like terms, we could say sine of 2A. So what we've just found is that sine of 2A is equal to 2 sine of A cosine of A. And that is what you'll typically see as a way to write the double angle identity for sine. So that's our first one. We'll go ahead and use the same process to talk about the double angle identity for cosine. So again, this will just be our first of the double angle identities. So now, here is the sum identity for cosine, another one we're familiar with already. And I'd just like to walk through it the same way we did the last one. So again, now, whereas in the past we would have understood A and B to be two distinct angles, we're just going to go ahead and put the same angle in twice. So now we'll go ahead and treat this as cosine of A plus A. And that means we'll get back cosine of A times cosine of A again, minus sine of A times sine of A again. And if we keep simplifying a little bit, we know that cosine of an angle times cosine of that same angle can be expressed as cosine squared of that angle. Sine of an angle times sine of that same angle would be sine squared. So far it seems like we could write cosine of A plus A, which is really cosine of 2A. We could write that as cosine squared of the angle minus sine squared of the angle. And this is in fact one of the forms for writing cosine of 2 times an angle. If you look at your trig identities handout, you'll notice there are two alternate forms of this identity, so I'd like to talk about where those come from as well. If this first form makes some sense, basically an easy way to arrive at the next two forms is going to be through the Pythagorean identities. Let's talk a bit more about that. So if I take the result that we already found, which is cosine of 2a equals cosine squared A minus sine squared A. But in place of that sine squared A, I replace that with its equivalent form from the Pythagorean identity. What would that form look like? We know from the past that cosine squared plus sine squared is equal to 1. So if I'm trying to isolate sine squared, that tells me that sine squared would be the same as 1 minus cosine squared. So right in the midst of this formula, I can replace the sine squared of A with 1 minus cosine squared of A. And if I spend a couple steps simplifying, I will arrive at an alternate form for cosine of 2A. Let's go ahead and take a couple more steps here. So if I simplify by, first of all, distributing this negative sign, we'll get back our cosine squared A minus 1, really plus cosine squared A. So if we collect the like terms there, cosine squared A plus cosine squared A makes 2 cosine squared A, and then we've got minus 1. So we have now arrived at a second form of writing cosine of 2A. And we'll see in a little bit why it's nice to have this alternate form. So I'm going to go ahead and bubble this off as another form you'll see on your identities handout. But there's yet another form. So if I asked you all to stop and consider where that third form might come from, what would you say? And hopefully, after a little bit of thought, we think again about that Pythagorean identity, which we know from the past, and using it this time around, though, to replace the cosine squared term. So from the Pythagorean identity that states cosine squared plus sine squared equals 1, if I keep cosine squared on the left and subtract sine squared, we now have a way to rewrite the cosine squared of A term in the original double angle identity. And I will go ahead and show some steps for that as well here. So what I'm going to do this time around is begin by writing the original cosine of 2A is equal to, but now when I see that cosine squared, I'm going to replace it with 1 minus sine squared. So that's what we're doing to the original double angle identity. The identity, of course, still says to subtract the sine squared. So I'll say minus sine squared. And then if we do a little bit of cleaning up, we'll notice that we have a negative sine squared and another negative sine squared, which combines to just a negative 2 sine squared. And this becomes the third and final form for writing cosine of twice an angle. So again, I'll just bubble this off. This is another form you'll see on your identity handout. So if we consider just briefly the value of these three different forms, let's just see what we can think about. The first form that we arrived at involves both a cosine squared and a sine squared on the right-hand side. This second form we came up with involves just cosine squared on the right-hand side. And this third form we came up with involves just sine squared on the right-hand side. So I would say that it will depend upon the information you're given to know which form of that identity you're going to use. And we'll see an example shortly. So just to summarize what this video was trying to point out is that the double angle identities that you'll have on your trig identities handout can be found through rewriting the sum identities. So moving forward, we are now going to take for granted that we have three forms for cosine of twice an angle. We have one form of sine of twice an angle. And I did go ahead and include the tangent of twice an angle identity here, although, as we've discussed in class, we can always just appeal to our knowledge of tangent in terms of our knowledge of sine and cosine. So I'll throw this idea out there as well. If I know sine of twice an angle and cosine of twice an angle, That's probably what I would use if I was asked to find tangent of twice an angle. I guess the last little comment here is you may notice from the identities handout, the angle is referred to as theta, so you'll see theta being used. In the examples I just worked through a moment ago, we were using the letter A, but it really doesn't matter. It's just referring to the angle and then twice the angle. So let's go ahead and try this out.